In this episode, we will talk about AdaCoT Pareto optimal adaptive chain of thought triggering via reinforcement learning. Okay, let's dive right into this. We all know large language models, or LLMs, have become, well, incredibly capable. They can write, code, translate. It's really impressive stuff.
Absolutely.
But when it comes to solving really tough problems, the kind that require complex reasoning, they often still need a little nudge. That nudge is often chain of thought or code prompting. It's the technique where you get the model to generate step-by-step reasoning before it gives the final answer. And the source material makes it clear this can dramatically boost performance on challenging tasks.
And that boost is significant, yeah. CoT can push these models much closer to expert-level performance in, say, advanced math or intricate coding problems.
Right.
But the critical challenge this paper really lays bare is the cost of that power. Standard CoT is indiscriminate. It generates those potentially long reasoning steps for every single query, no matter how simple.
Yeah, like the paper's example, what is 1 plus 1?
Exactly. You absolutely do not need an elaborate step-by-step process for that. This always-on approach is computationally expensive. It's highly inefficient during inference.
Which drives up deployment costs and adds latency.
Precisely.
And that inefficiency is a major hurdle, isn't it, for making these powerful models practical and affordable in real-world applications, especially the interactive ones.
It really is.
So the framework this paper introduces, AdaCoT, which stands for Adaptive Chain of Thought, is designed specifically to solve this. It allows the LLM to intelligently decide when to invoke CoT and when, a direct answer is just fine.
Exactly. Our mission in this deep dive is to really unpack the AdaCoT framework. We want to understand its core principles, how it actually achieves this adaptive behavior through training, what the experimental results show about its performance versus efficiency trade-offs, and, well, what it all means for the future of building more efficient LLMs.
Okay, let's double down on that problem first. The value of CoT for complex tasks is, like you said, undeniable. It helps models work through problems explicitly, leading to better results on things like hard math word problems or multi-step logic puzzles.
Right. The performance gain on the difficult stuff is well established, no question. But the core issue, the thing AdaCoT targets, is that this process substantially increases the number of tokens generated.
For everything.
For everything. And because standard ways of doing it apply it universally, it adds the significant cost overhead to all queries, including the vast majority, which are actually pretty simple. The goal, the ideal scenario, is adaptive reasoning.
The model itself figures it out.
Yeah. The model itself should be smart enough to recognize query complexity and tailor its reasoning process. Use CoT when needed, skip it when not.
The paper does mention some prior attempts to make CoT more efficient.
Right.
What kinds of approaches had researchers explored before AdaCoT?
Well, the source material outlines a few directions. Some work involved using things like length penalties or brevity rewards in reinforcement learning, RL, to try and shorten the reasoning steps after they were generated.
Okay, so making the chain shorter.
Right. Others focused on post-processing the Kogan output, maybe summarizing or pruning the steps after the fact. And some relied on more external controls, like explicit user instructions saying, use CoT now, or handcrafted rules to sort of toggle it on or off.
Okay, so efforts were definitely made. But the paper argues these had some pretty key limitations.
Crucially, yes. The paper highlights that these prior methods, well, they mainly focused on reducing the length of the reasoning after the decision to use CoT was already made. Or they used these non-principled external mechanisms.
They didn't tackle the decision itself.
Fundamentally, no. They didn't really address the core problem of adapting the decision to use CoT based on the nuanced variability in how complex a query might be. They lacked a unified, principled optimization framework, something that could systematically balance response quality against deployment cost across all kinds of queries.
And that brings us to AdaCoT's core insight, which the source grounds in formal mathematical analysis. How does it actually frame this adaptive reasoning challenge?
AdaCoT frames it as a multi-objective optimization problem. Basically, you have two primary competing goals. You want to maximize response accuracy or performance, let's call it P.
Okay, performance.
And you want to minimize deployment costs. The paper measures this using the CoT triggering rate, essentially the percentage of queries where CoT actually gets used.
So you want high performance and low cost, but those usually pull in opposite directions.
Yes. They absolutely do. And this is precisely where Pareto optimization comes into play. Instead of aiming for just one single best point, you're looking for a whole set of solutions that represent optimal trade-offs. That set is called the Pareto frontier.
The frontier. Okay.
Yeah, on this frontier, you can't improve one objective, like performance, without sacrificing the other, like increasing CASI usage and therefore cost, and vice versa. You can't get better on cost without maybe hurting performance a bit.
So it maps out the best possible compromises.
Exactly. AdaCoT provides a framework and mechanisms to explore this frontier. The paper describes the objective function structure conceptually as maximizing a weighted sum of performance minus a weighted sum of CASI usage. And these weights, equa P, T, they let you tune how much you care about performance versus cost.
That formal foundation seems really key to moving beyond just heuristics or simple rules. How did they actually train a model to achieve this kind of tunable, adaptive behavior? What does the training pipeline look like?
Right, so the pipeline involves two main stages. First, there's supervised fine-tuning, or SFT, and that's followed by a multi-stage reinforcement learning, or RL, process.
Let's start with the SFT stage.
Mm-hmm.
What was its purpose and how did they set it up?
The SFT stage acts as a crucial sort of warm-up. Its goal is to give the model an initial understanding of when COT might be beneficial, based on the query's characteristics. To do this, they prepared the training data using an auxiliary model in their experiments. It was an internal 15 billion parameter model.
Okay.
And this model automatically labeled queries. This labeling wasn't random. It was guided by these predefined principles, which they detail in Appendix B of the source, basically distinguishing queries that require in-depth thinking from those that do not require in-depth thinking.
Based on things like needing multiple steps or complexity.
Exactly, things like that. And using this automated, principle-guided labeling is more consistent and, importantly, more scalable than trying to do it all manually.
Makes sense. And how did they format the data itself to teach the model this distinction?
So for queries labeled as needing COT, the target response format was think reasoning steps, think answer. Pretty standard COT structure within tags.
Okay.
But for those labeled as not meeting COT, it was think answer. Notice the think tags are always there, but they're empty if no reasoning is needed.
Ah, so the structure is consistent, just the content inside think changes.
Precisely. That gives the model a uniform structure to work with. The result of this SFT stage is a model that's learned a foundational ability to recognize this structural difference and associate it, hopefully, with the type of query.
Okay, so SFT gives it the basic idea, the structural pattern. But the paper points to reinforcement learning, RL, as the stage where the really fine-tuned adaptive behavior gets learned.
Exactly right. The RL stage is where the model learns the actual policy for assessing incoming queries and making that dynamic decision. Do I trigger SOTI or not? This learning is driven by a custom reward function, RXR.
Okay, a reward function.
Yeah, designed specifically to capture that proto trade-off we talked about for a given input query X and the response R the model generates.
Can you break down the components of that reward function conceptually without getting lost in the formula?
Sure, think of it simply like this. There's a base reward, RBase, which just rewards the overall quality of the final answer. Is it correct? Is it helpful?
Standard RL reward for quality.
Right. Then there are specific penalties designed to guide the adaptive decision. There's a penalty, miss, if the model fails to use COT when it actually should have, according to their labels or principles. This is weighted by a coefficient COT.
Okay. Penalty for missing needed COT.
Then there's a penalty, Pover, if the model unnecessarily uses COT when it wasn't needed, weighted by S.
Penalty for overusing COT.
Exactly. And finally, a small penalty, PFNT, for any formatting errors, like messing up the think tags, weighted by OS.
And the key is those alpha weights.
That's the crucial tuning knob. By adjusting Eros and Eros, you effectively change the model's incentives. You steer it towards different points on that Pareto frontier. If you make error higher, you penalize missing arrows more, pushing it towards higher performance. If you make errors higher, you penalize overusing Caradom, pushing it towards cost savings.
So you can choose your preferred balance.
You can explore the trade-offs, and they used a specific, well-known RL algorithm called Proximal Policy Optimization, or PPO, to actually implement this learning process.
Now, training models in multiple stages like this, SFT followed by RL, can sometimes lead to, well, instability, right? The paper calls that a significant challenge they faced. Decision boundary collapse. What exactly is that?
Yeah, that's a really important point. Decision boundary collapse is a risk, particularly when you fine-tune a model on datasets where the distribution of desired outputs is heavily skewed.
Like in math.
Like in their RL math stage, exactly. Most math problems do benefit from POSI. So the danger is that the model, when exposed only to the skewed data during RL, might just learn to always trigger COSI, or in another scenario, never trigger it. It loses that nuanced ability to distinguish.
It just defaults to one behavior.
Right, it collapses into a single default behavior. It basically forgets how to make that adaptive decision it started learning back in the SFT stage.
Which would completely undermine the whole point of AdaCoT. How do they prevent that collapse from happening?
They introduced a clever technique called selective loss masking, or SLM. Its purpose is basically to protect and preserve the COSI triggering ratio and the decision-making distribution that the model learned in earlier, potentially more balanced stages, like the initial SFT.
Okay, selective loss masking. How does it work?
During the RL phases where the data distribution might be biased, like RL math, SLM selectively masks or ignores, the loss contribution coming from one single, absolutely critical token.
Which token?
The token immediately following the think tag.
Because that's the token that determines if reasoning steps are about to follow, or if it's an empty tag leading straight to the answer. It is the decision token.
Precisely. By masking the loss for that specific decision token on the skewed data, they prevent the reinforcement learning process from over-optimizing based on that skew and collapsing the decision boundary. It forces the model to kind of remember and utilize the more nuanced decision-making process it learned earlier.
That sounds like a really important stabilization technique for this kind of multi-stage training.
It seems crucial for ensuring robust and stable adaptive triggering, especially when dealing with specialized datasets during fine-tuning.
Okay, so they have the framework, the multi-stage training pipeline with SFT and RL, and this SLM technique to handle the collapse challenge. How did it actually perform in the experiments described in the paper? What was the base model they used?
The base model they used was an internal mixture of experts MOE model. It had 15 billion activated parameters out of 150 billion total parameters, so a pretty capable large model.
Okay, and MOE model. And the training followed that path. SFT, then RLNth using SLM, and then a general RL stage.
Yes, an RL general stage where they varied those alpha penalties, ARLs, to explore different points on the Pareto frontier.
And how did they evaluate the results? What metrics and data sets?
They used a pretty broad approach. For overall performance, they evaluated on 15 diverse public benchmark datasets covering lots of different tasks. Things like MMLU Pro, LiveBench, Math, Simple QA, ProcBench, even Olympiad Bench. They used an average score across these.
Okay, broad performance measure.
Then to specifically check how well the adaptive triggering decision worked on typical user queries, they curated a special 1,000 prompt daily use test set. And critically for the efficiency aspect, they measured the average number of response tokens generated on actual production traffic data.
Got it. So let's look at that Pareto frontier analysis first, the trade-off between average benchmark score and the COTI triggering rate. What did the baseline models show?
Well, the baselines behaved pretty much as you'd expect. Models trained without any COTI had low average scores. The SFT version got 43.6%, the RL version 47.7%, obviously at 0% COTI usage.
Low score, zero cost.
Right. Then, models trained to always use COTI had much higher scores. SFT got 58.5%, and the full COTI RL baseline hit 65.0%. But naturally, that was at 100% COTI usage.
High score, maximum cost.
Exactly. The adaptive SFT model, trained just with that initial stage, landed somewhere in between. A 57.1% score, using COTI about 61.3% of the time. A decent starting point, but not optimal.
Okay, and how do the AdaCoT RL models, the ones trained with the full pipeline and varying penalties, compare to these baselines?
This is where AdaCoT really demonstrated its value, especially in terms of the efficiency trade-off. By tuning those alpha penalties in the RL general stage, the AdaCoT RL models, they labeled them XT1 through XP4, traced out a superior Pareto frontier compared to just the adaptive SFT model.
Meaning better score-cost combinations.
Much better score-COTI rate combinations, yes. For instance, look at AdaCoT RL XP2. It achieved a 62.8% average score, which is pretty good, but with only a 53.3% COTI triggering rate on average across those benchmarks.
Wow, so that's close to the performance of the full COTI RL baseline.
Very close to the 65.0% score of the always-on RL model.
But using almost half the COTI.
Exactly. Nearly half the COTI usage on average. Other models like XP3 got a 64.3% score with 65.4% COTI, and XP4 hit 64.4% score with 67.7% COTI. So they get very close to that peak score of the full COTI model, but still using 30–35% less COT overall.
It really is a compelling trade-off.
Mhm.
Although it is worth acknowledging, as the paper does, that even the best adaptive models didn't quite manage to exceed the average score of the always-on full COT-RL baseline across all 15 benchmarks combined.
A slight gap at the very peak average
Yeah.
performance. Yeah, a slight gap. This might reflect the inherent difficulty in learning a single adaptive heuristic that's perfect for every task in such a diverse set. Or maybe it's just the RL optimization naturally balancing the score against the very substantial cost savings it can achieve on simpler queries within those benchmarks.
Okay, that makes sense. Now, shifting focus from the overall average to the adaptive triggering decision itself. How accurate was the model at deciding when to use COT on those typical daily use queries? And what did that test reveal about the decision boundary collapse issue in SLM?
Right, so on that curated 1,000 prompt daily use test set, the initial adaptive SFT model actually showed reasonable triggering performance to start with. It got an accuracy of 0.795 and an F1 score of 0.750.
Not bad for just SFT.
Not bad. But the ablation study they did on the RL math stage really hammered home the importance of SLM. The RL math model trained without SLM basically collapsed, just as predicted. Its accuracy dropped to 0.506.
Half right, half wrong.
Well, looking deeper, its recall was 1.0 and its precision was only 0.503. What that means is it was just triggering COT for everything in that math-heavy data set. It completely lost its ability to say no COT in it.
So it just defaulted to always on because the data pushed it that way.
Exactly. It succumbed to the skewed data distribution. In stark contrast, the RL math model trained with SLM performed much, much better. Accuracy jumped back up to 0.813, and the F1 score was 0.781. It successfully preserved the adaptive capability learned during SFT despite the biased training data.
That's a clear demonstration of SLM working.
Absolutely. And then the final AdaCoT RL models, XP1 through 4, showed how tuning those alpha penalties allowed them to further refine this decision boundary on the daily use set. Models like XP2 achieved a really nice balanced F1 score of 0.814, indicating it was good at both identifying when COT was needed, recall, and when it wasn't, precision.
So it learns to make the right call more often than not on typical queries. What does this improved decision-making actually translate to in terms of real-world efficiency gains when they tested it on production traffic?
This is where the rubber really meets the road. This is where you see the direct impact on resources and latency. Using production traffic data for that AdaCoT RL model XP2, the one with the good balance. They observed truly dramatic reductions in the COT triggering rates compared to the 100% baseline where COT is always on. On mobile traffic, the rate plummeted to just 3.18%.
Wow, from 100% down to just over 3%.
Yeah. And on PC traffic, which might have slightly more complex queries on average, it was still only 12.5%.
That's still a massive drop from 100%.
It's huge. And this translates directly, of course, to fewer tokens being generated. The average number of response tokens was reduced by 69.1% on mobile traffic and 70.6% on PC traffic compared to the always-on COT model.
Over two-thirds reduction in tokens.
Yes. And that massive token reduction directly means less computation needed, which means faster response times for users and substantially lower inference costs for anyone deploying the model. For applications where every millisecond and every token counts interactive assistance, real-time systems, this is a game changer.
Those efficiency numbers are really striking. They make the practical benefit crystal clear. Let's maybe discuss some of the design choices and the limitations they acknowledged in the paper.
Sure. The authors explain that their approach combining that initial principle-guided labeling for SFT with the subsequent RL fine-tuning was kind of a pragmatic choice. It gives the model a strong starting signal about cut A utility from SFT.
Gets it in the ballpark.
Right. And then RL refines that into a dynamic policy. Trying to learn that entirely from scratch with RL, especially figuring out the cost of skipping cut or the benefit of using it correctly, that's apparently quite challenging. So this two-stage approach worked well for them.
What limitations do they point out about the current AdaCoT implementation?
They're pretty upfront about several things. First, performance is naturally relative to the base model and the specific data sets used, so you might need some recalibration if you switch those. Second, the current COT decision is a simple binary. It's either on or off.
But reasoning isn't always black and white.
Exactly. Real reasoning is more of a continuous spectrum. Maybe you need a little reasoning, maybe a lot. AdaCoT currently simplifies this. Also, generalizing the learned COT policy across vastly different domains remains a challenge. What works for math might not be optimal for creative writing without further tuning.
Okay.
And the framework doesn't currently have built-in personalization. Maybe one user prefers very detailed answers, another wants brevity. AdaCoT doesn't adapt to that yet. And they mentioned the initial principle-guided labeling, while effective, could probably be refined further. Oh, and they also reiterate that slight performance gap at the absolute peak average performance point compared to the specialized always-on baseline.
Got it. One really interesting exploration mentioned in the paper is something called meta-reasoning. What was that about?
Ah, yes, meta-reasoning. During the SMT stage, they experimented with training the model to do something extra before deciding on COT. It would first output a brief sort of internal assessment of the query's complexity.
It's like thinking about the problem before solving it.
Kind of, yeah. Think of it as the model briefly thinking about how to approach the problem. The structure was something like think internal assessment text, to think followed by either the reasoning steps or the direct answer. You can actually see examples in Appendix D of the source. The model might generate text like, this is a simple factual question, or this requires step-by-step calculation inside those first think tags.
Okay, so it verbalizes its assessment. Did this explicit meta-reasoning actually help the adaptive decision?
Apparently, yes, quite significantly. Incorporating this into the SFT stage improved the COTI triggering performance noticeably on that daily use test set. They reported the F1 score jumping from 0.750 up to 0.840.
That's a big jump in F1.
It is. It suggests that making the complexity assessment explicit actually helps the model make a better subsequent decision about using COTI or not. And they also observed a cool emergent side effect: user controllability.
How so?
Users could sometimes influence the model's COTI decision just by including phrases like think step by step or give me a direct answer in their prompts. The model seemed to pick up on these cues, perhaps informed by its meta-reasoning training.
That user control aspect sounds really appealing. If it improved decision accuracy and offered that controllability, why wasn't this meta-reasoning used in the final RL models by default?
Ah, that comes right back to the primary goal: efficiency. The problem with that explicit meta-reasoning step is that it adds tokens to every single query because the model has to generate that internal assessment first, even if the final answer is direct.
Right, even for the simple questions.
Exactly. And given that AdaCoT, particularly Model XK2, achieved those extremely low QD triggering rates in production, like that 3.18% on mobile, adding this initial meta-reasoning step to all queries would actually introduce a pretty substantial cumulative token overhead. It could potentially outweigh the efficiency gains from the adaptive triggering itself.
So the cost of the meta-reasoning itself became too high at scale.
Precisely. So while it's clearly promising for decision accuracy and user control, the token cost of this explicit meta-reasoning method didn't quite align with their main efficiency objective in this particular framework. But they rightly highlight it as a really interesting area for future research, maybe finding more token-efficient ways to get the benefits of meta-reasoning without adding so much overhead.
That really illustrates the kind of practical engineering trade-offs involved. It also brings up another crucial question. Does training a model to be adaptive like this somehow limit its maximum reasoning capability? If you do need it to go deep, if you force an AdaCoT model to always reason, can it still perform as well as a model that was trained to always reason from the start?
This is a super important validation point, and they did test it. They used system prompts, or SPs specifically. They crafted an always reason SP to essentially force the AdaCoT RL models to generate COTM for every single query during evaluation, overriding the adaptive mechanism.
Okay, forcing COT on the adaptive models. What happened?
The results are in Table 3 of the paper. When forced to use COTI via the system prompt, the AdaCoT RL models were not just competitive with the full COT-RL baseline, the one trained to always reason, but in some cases they actually slightly surpassed its average score across the benchmark set.
Really? So the adaptive training doesn't somehow cap its potential high-level reasoning ability?
That's what the results strongly suggest, yes. It demonstrates that the adaptive training process, while successfully optimizing for efficiency on simpler tasks, does not seem to inherently restrict the model's peak potential reasoning capabilities. When a comprehensive step-by-step process is explicitly requested or needed, the AdaCoT model can still deliver top-tier performance. It maintains that ability while gaining all the efficiency for simpler queries.
That's a really encouraging finding. It means you don't necessarily have to sacrifice peak capability for adaptivity.
It seems you can get a lot of the best of both worlds here.
They also had kind of a neat side observation about long-form generation that came out of the SFT stage, didn't they?
Oh yeah, that was interesting. They noticed that the AdaCoT SFT models, even when prompted for long outputs using that always reason SP, seemed less prone to generating truncated responses or getting stuck in repetitive loops compared to a standard full-COT SFT baseline model.
Why would that be?
Their hypothesis is pretty intuitive. Because AdaCoT's SFT training data included many examples with those empty think tags for simple queries, the model saw many more examples of shorter, complete sequences during training. This might have inadvertently strengthened the learning signal for the end of sequence, or EOS, token.
Ah, so we got better at knowing when to stop cleanly.
Potentially, yeah. It might have improved the model's ability to properly terminate long generations. An unexpected but definitely beneficial side effect of the diverse training data used for adaptivity.
Okay, so to wrap things up a bit and put AdaCoT in context, how does it fundamentally differ from other prior work that was also looking at QD efficiency?
Well, as the paper discusses, particularly in Section 5, much of the prior work focused on actions taken after COT was already triggered. Things like compressing or pruning the reasoning steps to make them shorter, or using length penalties in RL to discourage overly long chains.
Optimizing the chain itself.
Right. AdaCoT tackles a more foundational problem: the adaptive decision of whether to invoke COT at all, based on the model's internal assessment of query complexity. It provides a principled, learned mechanism for a single model to make this dynamic choice internally. It doesn't rely on external triggers or focus only on optimizing the length of reasoning after the decision is made. It's about the decision point itself.
So AdaCoT really is a novel framework specifically designed for this adaptive triggering capability.
Exactly. By framing the problem as Pareto optimization, using RL with those tunable penalties to really explore the performance cost trade-off space, and critically incorporating SLM to ensure training stability and preserve that adaptive decision boundary, AdaCoT successfully implements dynamic kata triggering.
And the results speak for themselves.
They really do. The experimental results clearly show the impact. Dramatic reductions in computational costs and latency for simple queries because you avoid all that unnecessary reasoning, while importantly fully retaining high performance on complex tasks that actually require SCOT. This makes LLMs more efficient, more responsive, and significantly more cost-effective to run.
Which is hugely important for actually deploying these things widely,
Yeah.
especially in interactive and resource-sensitive applications.
Absolutely vital.
Well, thanks for joining us for this deep dive. It's truly fascinating to see how researchers are tackling these very practical challenges of making LLMs not just smarter, but also considerably more efficient and, frankly, economical to deploy.
Indeed. The whole concept of a model intelligently deciding when and how much it needs to think feels like a really significant step towards building AI that is both incredibly powerful and genuinely practical for widespread use.
Definitely. And maybe a final thought for you, the listener. Consider the implications of this kind of technology. How might adaptive reasoning fundamentally change the way we interact with LLMs in real-time applications day to day? And thinking further ahead, what new kinds of trade-offs or considerations might emerge as these models become even more capable and deeply integrated into our lives?